What if the proof was already sitting in a folder no one had opened in 20 years? Not a new discovery, not a fresh transmission from deep space, just an old file, forgotten, reprocessed by accident, because a graduate student didn't want to write a new algorithm from scratch. This is a story of how humanity found something it had already recorded and never noticed. Mara Okafor had spent 6 months building a tool nobody asked for. Her advisors wanted new data, fresh sky surveys, live telescope time, expensive and competitive, the kind you had to fight a committee for. Instead, Mara spent her nights doing something unglamorous, teaching an old machine learning model to look at archive radio data through a frequency band almost nobody had bothered to check. Not because she expected to find anything, because the archive was free, and free was all a second-year postdoc could afford. The data was from the Atacama Array, 20 years old, recorded during a routine calibration run that nobody remembered and nobody had reason to. Terabytes of it, sitting untouched on a server, because 2 decades ago, no one had the tools or the patience to search that particular slice of the spectrum. Mara had the tools now. What she had, more than anything, was the patience. She ran the model on a Tuesday night, mostly to test that it wouldn't crash. She expected static. She expected nothing. At 11:47 p.m., the console produced a single flagged anomaly, a signal, narrow, structured, repeating. She stared at it for almost a full minute before she let herself believe it wasn't a bug. Mara didn't call her advisor that night. She called Priya first, a friend from the data engineering team, someone who could tell her, fast and honestly, whether she'd made a mistake. "Run again," Priya said. "Different machine, different pipeline. If it's real, it survives." It survived. 3 more times on 3 different systems. The same 11-second pattern appeared, buried inside 20-year-old noise, at a frequency nobody had thought to search before. That was strange enough. What came next was stranger. Mara cross-referenced the signal's internal timing structure against the atomic clock stamped into the original recording. Radio signals carry more than a message. They carry a kind of fingerprint, a signature of exactly when and how they arrived, shaped by the motion of the Earth, the telescope, the atmosphere that day. The fingerprint didn't match the recording date. It matched today. "That's not possible," she told her advisor, Dr. Elias Voss, the next morning, sliding 2 printouts across his desk. "The file is 20 years old. The signal inside it is behaving like it's 20 hours old." Voss had built his entire career being unimpressed by young researchers with exciting theories. He looked at the printouts for a long time before he spoke. "Then either your data is corrupted," he said, "or something out there has been transmitting on a schedule so precise, it just so happened to line up twice, once, 20 years ago, when nobody was listening in the right place, and once now when someone finally was." "Which possibility scares you more?" Mara asked. Voss didn't answer right away. "The second one," he finally said, "because it means it wasn't luck that we heard it the first time. It was luck that we happened to be recording. And it means whatever sent it isn't done." The next 2 weeks were the strangest of Mara's career. She and Voss quietly requested time on 3 independent radio arrays, careful not to explain why, careful not to trigger the kind of institutional panic that turns real science into a headline before anyone actually understands what they're looking at. If the signal was periodic, if it really did repeat, they needed to catch it happening live, not buried in an archive. They didn't have to wait long. 9 days later, at 3:14 in the morning, all 3 arrays picked up the same structured pulse, in the same narrow band, arriving from the same patch of sky. It matched the 20-year-old recording almost exactly. Same internal pattern, same structure, not identical. There were small variations, like a voice saying the same sentence twice, with a slightly different breath in between, but close enough that there was no reasonable argument left for coincidence. "It's not a message," Priya said, staring at the overlapping waveforms on the screen. "Messages don't repeat exactly like this. This is a beacon." Mara nodded slowly. Something built to be found. But the real answer came from an unlikely place, not the signal itself, but its timing. Voss was the one who noticed it. He'd spent 30 years studying pulsars, the collapsed cores of dead stars that spin with regularity more precise than almost anything else in the known universe. When he mapped the interval between the two confirmed detections, 20 years apart to the day, against known pulsar rotation periods in that region of sky, one lined up almost perfectly. "They're not timing it to us," he said quietly. "They're timing it to a pulsar, a cosmic clock, something so stable, it barely drifts over centuries." "Why would you do that?" Mara asked. "Because a star can lie to you. A civilization can lie to you. A pulsar can't." Voss leaned back in his chair. "If you wanted to send something that any species, at any point in their development, could eventually verify as real, you wouldn't time it to yourself. You'd time it to the most honest clock in the galaxy." The room went quiet. "That means this isn't the first time it's happened," Mara said slowly. "If it's tied to a pulsar cycle that's stable, this beacon could have swept past Earth dozens of times. Hundreds, long before we had any equipment capable of hearing it. Or it could have swept past," Voss said, "while we did have equipment. And we just weren't looking in the right place. This is the part of the story that matters most, not the signal, but how close humanity came to missing it twice. The original recording sat in an archive for 20 years because nobody had a reason to reprocess it. It survived not because an agency prioritized it, not because a government funded a search specifically for it, but because storage is cheap and somewhere a policy said, keep the old data, just in case. And it was found not by a powerful new telescope, not by a breakthrough discovery, but by a researcher with limited funding, doing the least glamorous work in her field, going back to what everyone else had already decided wasn't worth a second look. "We didn't build a better telescope," Mara said later, in an internal briefing that would eventually become public record. "We just refused to throw anything away." Voss put it differently in the same meeting. "Every civilization capable of building a beacon like this had to make a choice," he said. "Broadcast something loud enough to be heard immediately, and risk being heard by the wrong kind of listener, or broadcast something quiet enough that only a patient species would ever find it." He tapped the printout. "This is quiet. It's not built for the strongest civilization in the galaxy. It's built for the one that doesn't give up on its own archives." That was the moment the team stopped treating the signal as a scientific curiosity and started treating it as a message with intent. Not, "Can you hear us?" but, "Are you the kind of species that keeps listening, even after everyone else stopped?" The final piece came from the content of the signal itself. It wasn't language, not in any sense a human would recognize as words. It was structure, a repeating mathematical relationship, the kind of pattern that doesn't require a shared alphabet, only a shared understanding of numbers and proportion. Buried inside it was something closer to an address than a sentence, a set of coordinates, encoded relative to the pulsar's position, pointing not outward into galaxy, but toward a much smaller, much closer patch of sky, well within the boundaries of Earth's own solar system. "It's not asking us to come to them," Mara said, once the encoding was confirmed by a second independent team. "It's telling us where something is. Here, nearby." Nobody in that room knew what that meant yet. Nobody claimed to. The honest scientific position, the one Voss insisted the team hold publicly against enormous pressure to speculate, was simple. "We don't know what's there. We know coordinates. That's all we can verify." But everyone in that room understood the shape of the moment they were standing in. 20 years ago, the signal arrived, and no one heard it. Today, it arrived again, not because the centers changed anything, but because the species finally became patient enough, curious enough, and stubborn enough to go back and listen properly to what it already had. "We didn't find them," Mara said quietly, near the end of that final meeting. "We finally became the kind of species they were waiting for. The pulsar that anchors the beacon's timing has a rotation period precise enough to predict, almost to the hour, when the next pulse should arrive. According to that calculation, the next transmission is due in under 3 years. No one knows yet whether it will repeat the same pattern, or whether, having confirmed that someone is finally listening, it will send something new. What's real? Radio astronomers really have raised concerns that SETI searches have historically focused on a narrow slice of the radio spectrum, potentially missing signals in a much wider, unexplored range of higher frequencies. Reanalyzing archived telescope data with newer, more sensitive algorithms is a real and growing practice in astronomy. Old datasets are regularly mined for discoveries the original instruments and software weren't built to catch. Pulsars really are among the most precise natural clocks known, stable enough that scientists already use them for deep space navigation and timing experiments. What's scientifically possible? A civilization choosing to time a beacon to a pulsar's rotation, rather than to its own clock, is a serious idea that has appeared in real scientific proposals about how to make an interstellar message verifiable across enormous timescales. The idea that older, unprocessed data might contain undiscovered signals, simply because no one has reanalyzed it with modern tools, is a genuine and active area of astronomical research. What's speculative? Whether any such beacon exists, whether it would specifically reward patient reanalysis of old data, and whether it would encode coordinates pointing to something within our own solar system, are all speculative ideas, plausible in concept, but with no evidence behind them today. What's fiction? Mara, Priya, Voss, the specific signal, the specific discovery, and the coordinates it points to are entirely invented for this story. Final verdict. The science behind how this discovery happened, the overlooked frequency range, the reanalysis of old data, the use of a pulsar as a timing anchor, is grounded in real, current scientific thinking. Whether anyone is actually out there sending something is, and remains, one of the biggest open questions in science.